Alright, so we already did logarithmic when we did 5.1 log derivatives, 5.2 log integration. Okay, what we're going to focus on today and tomorrow is exponential. Specifically, we're going to do the derivative of e to the x, which we actually did in December. Alright, I didn't do it so that you would remember it this whole time. I just wanted to kind of get you exposed to how to derive e to the x. Okay, before we really get into that though, I want to kind of just review how is e to the x related to natural log of x. Okay, so if this says find the inverse, I'm just going to give it to you. We've talked about this before. Natural log of x and e to the x, they are inverses of each other. That tells us a lot about e to the x. For instance, the graphs, how are the two graphs related? Natural log of x and e to the x, they're inverses. Remember? So there's e to the x. This would be natural log of x. And you see a relationship there. Anybody? I'll help you out here. They are a reflection across the line y equals x. Basically, with inverses, all the x's become y's, all the y's become x's. So remember, the domain of natural log was 0 to infinity. We went over that last week. That's now the range of e to the x, and we can see that here on this red graph. Bottom to top, the range would be 0 to infinity. All right? The range of natural log was all real numbers. Well, now that's the domain of e to the x. Okay, the reason this is important is because we need to know that we can take e to any power. We can take e to any power. Any power. Positive, negative, fraction, 0, whatever. The range helps us because this tells us that no matter what, my result will always be positive. So e to any power is a positive number. It may be a really big or really small number, but it's still positive. Okay, we know that this function's continuous. We can see that just by looking at the graph. We know that this function's increasing. I can see it on the graph, but what does that tell me about calculus if the function is increasing, specifically about the first derivative? Positive, right? Okay, 1 to 1. This means that every x has its own special y, and every y has its own special x. There are no, like, repeats for x's or y's. All right, this graph is concave, what do you think, looking at that picture? Concave up on its entire domain, which tells us that the second derivative is also positive. Okay, so not only are the y values positive, the first derivative is positive, and the second derivative is positive. And if we kept going, all of that would be positive. All right, now we got some limits here, but I don't want you to think, how did we do limits? Just think about what is a limit. A limit is saying when x is really close to this number, what is the y value getting really close to? So looking at this graph up here, when x is approaching negative infinity, that would be the left part of the graph. Okay, this other one's going to be the right part. When x is approaching negative infinity, what is y approaching?
0.
0. So we can say that the limit then equals 0. Okay, we also call that end behavior or horizontal asymptote. Okay, what about the right side of the graph? When x is getting really, really big, what is y doing?
Infinity.
Getting big as well, so we say infinity. Okay, you could have also said does not exist, because a limit that equals infinity doesn't exist. All right, so that's just a little bit of review. Okay, let's solve a couple of equations. This is going to pop up from time to time, and I want you to feel comfortable with it. Okay, first off, we have an exponential, and then we have a log, and we're really going to solve them in very similar ways. We're going to rewrite them. So we see that 7 equals e to the power of x minus 1. Or is that x plus 1? Sorry. So we're going to rewrite it. Now, do you remember how to rewrite an exponential into a log? Does it sound familiar at all? Log base e. and then you flip to the other side, of 7 equals x plus 1 equals the power. Now, log base e, that's the exact same thing as natural log. ln natural log is log base e. So then, remember, we're trying to solve for x here. So x then is just going to be natural log of 7 minus 1. And if you wanted to get a decimal version, you could break out your calculator and do that. So to solve an exponential equation, you rewrite it as a log, and you solve for x. So what do you think we're going to do to solve a logarithmic equation? Can we rewrite it? What is ln the same as?
Log base E.
Log base e. That's where we're really going to start. So I'm going to start with the e. E, which is the log base, to the power of 5 equals this log argument, 2x minus 3. So then what does just x equal? So you'd add over the 3 and divide out the 2. And again, you could break out your calculator and solve there, okay? Really, except for the limits, all of this is stuff you did in Algebra 2 and Pre-Calc. I know you don't remember everything, that's why we go back over it, that's why we review it. Okay, now for the really important part, okay? This is actually the easiest part too. The derivative of e to the x is e to the x. It doesn't change. Alright, which makes it the easiest thing to take a derivative of, I think. That also helps explain why this graph is positive. The first derivative is positive because it's just the same graph. Second derivative is positive because it's just the same graph. At any point along this curve, whatever the y value is the same as the slope, and it's the same as the concavity. That's unique to e to the x. There's no other function that does that. Whoops. Let me go back here. Okay. So that's nice if you have just plain old e to the x. But what if you have e to some more complicated power? Well, it's almost just as easy. It's still just e to that same power, but then you got to use chain rule and say times the derivative of the power. Do y'all remember this at all from December? It's okay if you don't. It was that same week I taught you guys about L'Hopital's rule for the exam. Okay, find the derivative. All right. So y prime is going to equal. Okay, this is not just e to the x. It's e to something more complicated. But we're just going to rewrite it times the derivative of the power. So what would I multiply by? 3. And that's your answer. And we, of course, could move the 3 to the front if we wanted to and make it 3e to the power of 3x minus 5. Okay? So, on number 4, I kind of need to rewrite this. I need to rewrite it so that the power is not a fraction, because I don't really want to do quotient rule if I don't have to. So how could I rewrite this power? -7. Perfect. That's going to make this problem easier. So then y prime would be e to the power. You just rewrite it. Okay, rewrite times the derivative of the power.
Oh, no,
Positive 14x to the -3. And that is your answer. I know it's confusing to go back and forth between derivatives and integrals. It will get easier, but it's probably the most confusing part about this semester. All right, number 5, relative extrema. What's the first step if we're going to find maxes or mins? Cry. How about find the derivative?
Yeah.
Okay, what rule do we need to use to find this derivative? Product rule. So derivative of x is 1. Then we just write e to the x, right? Plus, then we write x times derivative of the second part. Now, remind me, what's derivative of e to the x?
E to the x.
E to the x. Okay, now, we're going to think, where is this derivative undefined? So what do you think? Where is this derivative undefined? Is there anything I can't do e to the power of? Or can I do e to any power? Like I get, some of you are thinking about the domain and range, but what I'm saying here is there any x value that I can't use?
No.
Or can I use all the x values?
Yeah.
I can use all the x values. Now my result is always going to be positive. So this derivative is not undefined, so we just set it equal to 0. It's where's the first derivative undefined, cusp, most likely, or where's this derivative 0? That would give us like a curve, a max, or a min. All right, so we got a factor. So what can we factor out? E to the x, and I'm left with 1 plus x. So now I'm going to set each factor equal to 0. And if e to the x equals 0, what is just x equal? Okay, there's a couple ways to think about this. One thing was e to the x is always equal to a certain type of number. Okay, so, or let's go with that. Let's rewrite this as a log. It would be log base e, which is natural log of 0. So what's natural log of 0? Don't say 1.
0.
It's not 0 either, but at least you didn't say 1. Why do people say 1? Because natural log of 1 is 0. But natural log of 0 is not 1. Okay, fill in the blank. You can only take natural log of
A positive
a positive number.
0 is not a number.
0 is not a positive number, therefore this is a dead end, and we don't have any critical numbers. But we had to go through that. Now next time you see this is going to happen a lot with these relative extrema. You're going to hit e to the x equals 0, and next time you may not remember it right away, but you'll figure it out, and then the time after that, it'll be just something you know. Maybe it'll take 4 times, but... Alright, so our only critical number is x equals -1. So I put that on a chart, a sign chart, and so I take a number to the left of -1, say -2, and I plug it into the derivative. Now I'm going to plug it into the factor derivative, because if I do that, remember e to the x is always positive, so I really don't even have to plug it into that piece. 1 plus -2 is negative. Okay, therefore the function is decreasing to the left of x equals 1. What happens if you pick a number that's greater than -1? Like, say, 5. 1 plus 5, that's positive. So we have a relative min at x equals... We're just going to keep reviewing this stuff, by the way. This whole, like, relative extrema tangent lines, like, all that, we're just going to keep doing it, keep doing it, keep doing it. Okay, number 6, last problem. You ready?
Yeah.
It's probably the easiest one on here, I think.
No.
I guess you can use your calculator. For 1970 to 1990, the number of medical doctors can be modeled by this exponential growth. That makes sense. There's always more and more doctors every single year. T equals 0 is 1970. At what, really focus on this word, rate, was the number of doctors changing in 1988. What is rate code for? Slope and derivative. Exactly. So we are going to find the first derivative. Now, we could do this by hand, or we could do this on our calculator. Remember, we can go F3, differentiate, 348, 000. Diamond x is e to the power of, I'm going to go 0.033666 x. Close that parenthesis, comma x. Y'all stay with me here. We're almost done. All right. We could have, this is going to give us kind of a weird, I didn't do this in my other classes. We could have done this by hand, and now I'm kind of wishing that we had done it by hand. I wasn't expecting that. I know. I should have done this in my other classes. Here, let's do this by hand.
Okay.
You just rewrite it. Remember, you just rewrite it, and then what do you multiply by? The derivative of the power.
Yeah.
So we go times 0.033666. Now that's in general. What do we need to do to find what is this rate of change in 1988?
Plug in 18.
We need to plug in 18 right there. So this for sure is where we want to use our calculator. So down here, I'm just going to go 18, store that in for X, go back up here. It's messy, but it's the same, it's equivalent to the same thing that I've written. And there we get our answer. Okay? 21,475.734. With the units here, MDs per year. Okay, we're going to continue this tomorrow. And I'm